Welcome to today's day in history, March 20th, 1916. Now, today is the day that Albert Einstein submitted his Foundation of the General Theory of Relativity for publication. Now, I'm going to try and explain the general theory of relativity to you today. So, it might be a little complicated. But the big idea is this. The big idea is that we often learn from things we've done in the past. Seems like a fairly simple, big idea. But if it wasn't for the work that Einstein did 10 years before, the general theory of relativity would not have come out in the way that it did. Now, we are in Berlin. This is where Einstein was working at the time. And next. Now, we've talked about Einstein before. We talked about the year that he moved to America when Nazi Germany was taking over. And during that day in history, we talked about some of his works, and we talked about space-time and the fabric and barospheres and gravity and all this cool stuff. But we didn't really talk in detail about any of those specifically. So today, we're going to talk about the general theory of relativity. Now, this is different than special relativity. But to be honest, it's all kind of confusing. But I'm going to try and simplify it. So let's see what we can do. Now, let's imagine you're driving a car. You ready? Here we go. I'm going to drive a car. Okay. Now, I'm driving a car. And if I say, take this pencil and I throw it in the air while I'm driving a car, going like 50 miles an hour, the pencil, me, everything is going the same speed. Now, if I were to turn real fast, and this has happened to you, you've been sitting in your car and your parents are driving, and then all of a sudden they go around a corner, and what happens? Everyone goes, woo, right? So the motion changed, the speed changed, but if I'm just going 50 miles an hour, I throw my pencil up in the air, my pencil comes right back down. Now, if I were to throw it up right as someone slammed on the brakes, the speed would change. And what would happen is something like this. Okay? The pencil would go flying. Yeah, I know. Now, so if you're driving and you look out the window and you see a tree, that tree is flying by, right? Now, if there's somebody standing by that tree and they see you, you're flying by. But both of you don't feel like you're moving. So, here we go. Now, the Earth is spinning at 1,000 miles an hour. It feels like we're just sitting here, but the Earth is actually going 1,000 miles an hour as it spins. Now, the orbit of this, as the Earth goes around the sun, is going 67,000 miles per hour. So we're moving two ways. Okay. Now, not only is the Earth moving, not only is it moving around the sun, but our entire solar system is going around the Milky Way galaxy at like 500,000 miles per hour. So we're always moving. Now, let's switch to Einstein. Well, another way we can think about this, I got my slides backwards, but that's okay. We're just going to keep going. I'm going to do this in one take. I don't need to cut it. So let me give you another example, because it's kind of confusing. Imagine you're walking on one of those escalators or not escalators, but those like walking sidewalks at an airport. Have you ever seen one of those? Yeah, I know. Yeah, they're pretty cool, huh? Especially if you run on them. It's kind of like an escalator. But imagine you're walking on one, and the moving sidewalk is going 3 miles an hour. And there's somebody off to the side that's watching you. If that person off to the side watching you, they see you going 3 miles an hour if you're standing there. Okay? But for you on the moving sidewalk, you're not actually moving. You're just standing still. Now, let's imagine that person decides to walk 3 miles an hour on the moving sidewalk. The person off to the side now sees you going 6 miles an hour, whereas you are going 3 miles an hour. Now imagine this. Imagine if I turned around and I walked backwards 3 miles an hour, I would be walking 3 miles an hour, but the person seeing me from the side would see me going 0 miles an hour. 3 minus 3 equals 0. So it's a little confusing. Let's go to the next slide. Now, today, March 20th, 1916, is the day that Einstein actually published this theory. And I did a search on the internet and I found it. And I read through it, and I didn't understand it because it was in German, but it looked pretty cool. But it changed a lot of things. Let's go to the next slide. Now, here, this equation, I'm going to explain it to you. Actually, I'm not, because it's really, really complicated. There's tons of variables, there's speed of light, gravity, there's all kinds of stuff. But I just want you to see that there's a lot of complex math involved. Now, if you think this is complicated, look at this equation. There's parentheses, and the W doesn't stand for water, probably. So, next one. Now, okay, here's where it gets interesting. Now, there's something called Euclidean geometry, and this is the geometry we do in class. This is the geometry that says two parallel lines will never meet, right? We talked about that. We had a lesson on that. Remember the two people that just had straight faces and they're walking along the lines because they never get to meet anybody? And then there's the divergent and the convergent, and they're happy and they're sad. Well, Euclidean geometry says that two parallel lines will never meet. Euclidean geometry also says that a triangle's angles equal 180 degrees. So no matter what triangle you make, if you add up the angles, if you measure them, it'll equal 180 degrees. Pretty cool, right? Now, the universe doesn't follow Euclidean geometry. So, go to the next slide. Now, if we look at space-time, and we've talked a little bit about this. I think I got somebody's coat and I put like some marbles on it. You guys remember that? And we stood around it and we watched it all. Well, pretty much what happens is space, the space that we live in, and the time it takes things to happen are like one thing. People describe it as a fabric. And this picture really helps, okay? Now, the Earth has so much mass that it actually sinks down into space-time, so that if you were to take two lines, let's say two lines of light that are parallel, and they're going through space-time, when they get to gravity, when they get to something that has gravity, they actually bend around it, okay? Which means two parallel lines could meet, okay? Let's go to the next slide. Now, you see, these two lines were parallel, but they ran into mass in space-time that changed the shape of space-time. And so those two parallel lines end up meeting. It's kind of crazy. Next slide. Now, there's another thing where, let's say you have two identical twins, and one of them decides to go to another star system that's like going to take 20 years to get to at like 90% the speed of light. Now, if the one twin says, well, I'll see you later, and the other one gets on a spaceship and flies off, and they're going that fast, what's going to happen is that the astronaut that's flying through space is actually going to age slower than the twin that's on the planet because of how fast they're going and how they're traveling through space-time. It's really complicated. And there's actually a lot of really cool videos that you can watch that try and explain it in a simple way. But it's really a complex thing. Let's go to the next slide. Now, we talked about this. I can't remember, did we talk about it this year or last year? You forgot to? Yeah, I forgot to. But we did talk about the LIGO at one time. And the LIGO is this amazing experiment that was able to measure gravitational waves in space. Now, they have two locations, one in Livingston and one right near us in Hanford. And one of these years, I'd love to go on a field trip there. But pretty much what they do is they shoot giant lasers down tunnels, and then they measure the vibrations of those lasers as they bounce off mirrors. I'm sure it's way more complicated than that. But it used many of Einstein's theories of special relativity and general relativity to help explain that these things actually exist. So, just recently, we actually proved some of Einstein's theories based on these two experiments. Really cool stuff. Now, we're going to end with a black hole because there is a lot of interesting stuff that Einstein came up with, and a lot of things that he came up with tried to explain these really complicated ideas. And one of the things that's really hard for, I think, humans to understand is the idea of a black hole, of something that has so much weight, so much mass, that not even light can escape. And so what is there? I don't know. But if you decide to be a physicist, it could be you that writes the next general theory of something really important.